Jacob's Ladder is a simple tool designed to investigate how users understand the relationship between filtering sets of nodes in a graph and pivoting from one set of nodes to another. For these examples, we use a dataset about American football from 2013, the most recent year this data was freely made available. Jacob's Ladder includes a search box with suggestions below, indicating sets of nodes whose attributes match the query. Notice that both aggregate and individual matches are shown above and below the line. This allows a user to either begin their exploration with a general set of nodes across a category, or they can begin with a single specific node. In this case, we select a football team. We can perform a pivot from the node we just selected by returning to the search box. Now we are searching only among the nodes that are connected to our most recent selection. We can continue by selecting all player nodes associated with Florida State. On the left side of the screen, some basic information about the current set of nodes is shown. We can group nodes by their attributes. We can also sort the histogram by descending value, ascending value, ascending count, or descending count. Here we filter the players so that we only work with the wide receivers on the team. If we only want to see the receivers that have touchdown receptions, we can perform an additional pivot to see how those players performed in each game. Filter by touchdown receptions, and return to the player nodes to see that we only have 3 players selected out of the original 15 wide receivers. The top of the interface shows the series of filters and pivots that we've enacted to arrive at the current set of nodes. Starting with the Florida State team, we pivoted to its wide receiver players, then performed what we call a connective filter of player nodes through their connected statistics nodes. As we outline in our paper, informal user testing with this tool helped us identify the only point in a series of pivots where the user's intent is ambiguous. For example, we can snip all the downstream pivots below the team and now swing out to game nodes representing all the games that Florida State played. If we then pivot to team nodes, we might expect to see the set of all teams that played in those games, including teams that played against Florida State. However, the filter that we initially enacted is still in place. We can only pivot back to one team, Florida State. The interface allows us to fan out globally by toggling a scope button. Alternatively, filters can be removed directly by snipping them. As we discuss in the paper, user testing with this tool confirmed that this ambiguity is a real problem when pivots and filters are combined, and these tests also narrow down the precise corner cases where this ambiguity arises. Additionally, our tests expose an opportunity to resolve these ambiguities automatically that we refer to as smart pivoting, which we hope to evaluate directly in future work. Pivots have another important implication for future visualization research, because they are a very simple way that users can directly indicate semantic meaning in the data. For example, let's imagine that we want to know which team's home stadiums have an AstroTurf surface. We can select all of the stadiums in the dataset and filter to just the stadiums with AstroTurf. If we then swing out from stadiums, we can see that this particular database does not connect stadium nodes to their home teams. Instead, we can only pivot to games. While the user can still answer their question by pivoting from games to teams, it's clear that this kind of question is more difficult to answer because the underlying data abstraction was not designed for it. It's easy to see how a sensible engineering decision might have resulted in this problem. Some football games, such as championship bowl games, are played in neutral stadiums that are not associated with either team. It makes sense then, in designing the database, to only connect stadiums to games and not to teams, to avoid these corner case exceptions. However, as this example shows, such a data abstraction may not accurately map to users' tasks. In this example, if a system records users frequently pivoting from stadiums to games to home teams, it could respond by adding edges to the graph, directly connecting stadiums to their home teams. This kind of adjustment could make data abstractions more relevant to users' tasks automatically, without relying on a database engineer to fully anticipate all user tasks in advance. And we plan to implement and evaluate adaptive data abstractions such as this in future work.